So without further ado, it's very nice, a great pleasure for me to be able to introduce Zhijing Jin, who is an assistant professor at the University of Toronto and postdoc at the Max Planck Institute in Germany. She is an Ellis advisor and will also be a faculty member at the Vector Institute. And her research focuses on causal reasoning with LLMs and AI safety in multi-agent LLMs. She's received 3 Rising Star Awards, 2 Best Paper Awards at Europe's 2024 workshops, 2 PhD fellowships, and a postdoc fellowship. And more information can be found on her personal website. I also encourage you to check out Zhijing's new lab at Toronto, which seems to be growing and doing more and more every time I look at the website. That is it. And yeah, Zhijing, if you wouldn't mind just advancing the slide. Yep, so just as a reminder to everyone else who hasn't been here before, this is our kind of regular cooperative AI seminar series. So we'll be thinking in the seminar series about some of the kind of bigger picture ideas, as well as the kind of later developments that are going on within the field. So Zhijing has been one of those people working on some of those later developments and is going to present kind of a few kind of interesting results here about kind of cooperation and conflict and so on in the context of language model agents. And yeah, the emphasis is also on critical discussion. So we'll make sure there's plenty of time at the end for some Q&A, which I'll be helping to mediate. And yeah, I think that is basically it. I just have one more thing to mention on the next slide. So just as a very quick advertisement, some of you may already have seen, but AI Safety South Africa is running a cooperative AI fellowship this coming winter, so starting in January. And Zhijing is one of our amazing mentors for that fellowship, along with many other amazing people from places like Google DeepMind, MIT, CMU, all of these great places. So applications for that close at the end of the month. I believe applications are due in by the 28th of September. So if you want a kind of fully funded kind of research, kind of mentorship program in South Africa working on cooperative AI at the beginning of next year, then I very much encourage you to apply to that. There'll also be an information session for people who are interested in applying and want to learn a bit more, which is happening next Thursday, I believe. But all the details of that are on the website. If you just type in Cooperative AI Research Fellowship, you'll find it. In fact, Natalia has just posted the link in the chat. That is everything from me. And so now, I will hand it over to Zhijing. And thank you very much for joining us.
Hey, awesome. Thank you so much for the warm introduction, and definitely looking forward to both the research fellowship in South Africa and all the many programs of SAFE. So today we will talk about, do LLM agents cooperate? Insights from our works GovSim and SanctSim. I'm Zhijing, and today my student David Guzman also joins me on the call, and we will be open to join the discussions in the last 20 minutes of the talk. So getting started, we will first cover our work on GovSim, Cooperate or Collapse, Emergence of Sustainable Cooperation in a Society of LLM Agents, also in collaboration with Giorgio, Max, Benhad, Rimaya, and Radha. So the driving problem here is that we might soon, or we are already living in a society with multiple AI agents playing different roles, maybe some doing things relevant to sales, some doing things relevant to education, and of course, many other areas of our work. However, we have the alarming signal from the study of the human side on cooperation that there could be a potential risk of the tragedy of the commons when people share the same pool of resource. And just to have a recap, the classic problem in the tragedy of the commons is overfishing, where it sort of distills the problem. Let's say if we simplify it in 2 fishermen's scenario, and each fisherman can have the action of reserve the lake or overfish. Then, although we know that reserve is probably the best for society, but whenever one of the human agent defect then it can get a bit more reward, let's say for A this case, and less reward for B this case, and symmetrically. With this tendency, everybody has a motivation to defect, therefore ending in the overfish scenario, which is worse for both of the fishermen. So the underlying structure here is that although the best group outcome is reserve, the reality often leads to the natural equilibrium of a defective society. So this phenomena has also been shown in the overgrazing scenario and climate change. And the reason why we call our work GovSim is that we're really inspired by the Governing the Commons work by Eleanor Ostrom, and established such an LLM society driven by the question, like how would a society of multiple AI agents be like? And we sort of instantiated by using LLMs to role play different agents in these classical studies. Let's say we instantiate John, Kate, Jack, and many other fishermen. Then giving a shared lake, the key question here is who should fish how much over a time period. And we further established the environment to show the diversity of the settings to be a fishing village with different fishers, a pasture with different shepherds, and a pollution setting where there are multiple factory owners sharing a river. And the context of this work is really also evolving from the previous game theory setup, where the whole setting is purely formal, numerical, and it's more mathematically heavy domain to calculate what is the Nash equilibrium and so on. Or the next stage in adding deep reinforcement learning, where making agents to learn the dynamics of the game. And then what we do here is really like put LM agents in the scenario, so we can be open for a much diverse action space, and also we can allow communication among the agents. So our entire simulation here spans over 12 months and in a virtual village. And here, to set it up, we share the fishing lake that has fish, for which in the end of each month will double up to 100 tons. And then within each month, we have the action, discussion, reflection stage. Just to show an example, in the beginning of each iteration, each monthly iteration, we have a world announcement, such as there are 100 tons of fish, and describe how the environment works. Second, in the action stage, each fisherman sets off to decide a number of fish to catch. And then in the middle, in the discussion phase, there could be, let's say in this case, a blaming over an overfishing agent, saying that Jack caught more fish than all the other villagers. Then moving to the reflection stage, we might see positive behavior of agents really reflecting and reducing the number of fish. Or there could also be, in other cases, revenge behavior, where agents will get all the fish in the next month and probably the simulation dies immediately. And then things go on for the next iteration and so on. So just show an example of our act, discuss, reflect agent architecture. So basically, to implement it, we also set agent's memory to have observation, reflection, and action. And for example, right before the action stage, we show the agent's memory, such as the initialization of the world. There are 100 tons of fish, and it's before everyone fishes. And then the action stage basically tells it okay, here's the remaining fish range, and decide a number of tons you want to catch this month. Then moving forward, in the reflection stage, for example, it's sort of after the agents talk with each other in a bit like a town hall discussion. Then in the reflection stage, it will be like summarizing what has happened in the discussion, and then maybe the community agreed on a maximum limit of 3 tons of fish per person in the next month. Then what key insights have you developed, and what do you want to do in the next month? So bringing this forward, we can see some results from the time when we tested for this NeurIPS 2024 work. So we tested a range of models from open weights to closed weights, and report a set of metrics from overall the survival rate, namely how many agent society live until the end of the calendar year without depleting the lake or resources. And then here we found that even the best model survives less than 54% of the time. And most other models, especially open weights and slightly weaker models, all have 0% survival rate. This is further exacerbated, sort of highlighted by showing the survival time, namely the number of months when the resource is still available and not depleted. And then we found that most agent societies actually die out in the first month with a survival time only 1 month. And the best one fails on average at the 9th month. So moving this forward, we really center at 3 different types of subskills in the further analysis of the paper. The first one is mathematical reasoning. Namely for a really sustainable multi-agent society, and maybe even for human society, there's a lot of popular science work telling people knowledge about the climate change. And then in this case, it will be like moving to LLM society. Do these agents really know what will happen if they keep doing a certain number of fishing? And then in the second pillar, it's about morality, because sometimes you're comparing apples with bananas. Namely, if there's a certain action that contrasts self-interest and group interest, do they want to do a bit more about it themselves, or a bit more caring a bit more about others? And then the other type of trade-off is also tricky in that do they care about the harvesting this month, or in the future accumulated in general, short versus long term? Lastly, there is also communication, namely, can safe agents persuade non-safe agents? So we will show a preliminary analysis from this paper and show a much deeper investigation in the following SanctSim paper. In our preliminary analysis using GovSim as an example, the math pillar basically distills the pure, a little bit like GSM 8K type of arithmetic questions, saying that maybe we start with 100 tons. If each fisherman catch 20, can you already predict how many fish will there be next month? And hopefully, if agents can see the future accurately, they should be able to avoid it. By the point of GovSim, a lot of models which didn't survive the whole simulation, it has a correlation with their poor mathematical reasoning, with, let's say, some of them only 20% accuracy out of 100% on certain reasoning cases. But then in the SanctSim, we'll further show what's the relation between reasoning and further their moral choices. In the morality pillar that we highlighted, we basically look at like sort of self-benefit and the group benefit, and further trying to intersect math and morality by universalization of like 11-2020 work. And we specifically add the additional information in the prompt introducing that now if everyone fishes 20 tons, the lake will deplete. What's the further action that you want to decide? And here we observe that the survival time actually increases on average by 4 months. And then further moving forward, the last pillar on communication, we also did ablation study of removing the whole discussion stage versus keeping it. And we see sort of evaluate overusage and a couple of other metrics. And for example, on average, we see communication saves resource overusage by 22%. And this is especially a case where we further want to investigate and has a preliminary setup of having, because our previous society is pretty homogeneous, and we did prompt an agent still with the same backbone, like the LLM engine, but prompted to be a greedy newcomer. And we observe how the number of fish destabilize in the beginning, and then it might lead to either the society collapse or in some case it could recover. And that can attribute a lot to the discussion stage. Sort of moving this further, we're also very excited to introduce our further work that brings some of the questions from the 3 pillars to further investigation using the context of like inspecting free riders in public goods game. This is accepted as column 2025 paper, which we will present in Montreal next month, and also oral paper in the workshops at ACL 2025, which we also presented this in Vienna. So David and Yongjing and many of our collaborators, we together look into the question of like reasoning models, and because of their improvement in math, coding, and many others, what does it mean for cooperation tasks? And specifically in this study, we look into, can LLMs pay a personal cost to enforce cooperation? And just to set this up, we specifically look into public goods game, for which a reason we will introduce later, but also just to motivate it. Let's say that in more and more settings of LLM multi-agents, let's say if we have a cloud-side coding agent that uses multiple agents from different sources to co-maintain an open source library that thousands of other agents depend on. And although there are task division, it could be totally possible that one of the agents could quietly skip documentation or skip testing the environment or skip certain coding tasks, and then making the whole ecosystem rot. The other case could be that, for example, for many of us who know federated learning, let's say if it's sort of a way to preserve privacy. Let's say that if there are multiple hospitals who share patient data to update the model weights on their side, but keeps the data in the hospital. But it could also be that some of the agents don't want to contribute and let the others pay the time and efforts, collected the data, improve the model, upload fresh gradients. And then holding such data back can boost local privacy and efforts, but also degrade the community-wide accuracy. So here we basically are in these situations where if they cooperate, the common resource thrives. If they don't, then the shared resource degrades. And then now we basically give LLM agents further a choice where they can decide whether to sort of give others punishment or join a community where punishment is possible. And to test this, we basically set up an experiment that follows the human society, which has an experiment and the reporting in the 2006 science paper on the competitive advantage of sanctioning institute. So basically, we set up the same environment, but with LLM agents. So we initiate 7 different agents and keep the same number of rounds as in human studies, so 15 rounds. And in each round, we have 2 stages. The first stage is the pure public goods contribution, where each agent can pay a certain number of tokens to a public pool, and it has equal share to everyone after a productivity rate. And the free rider problem here in the first order is basically it's the most beneficial for each individual to not contribute anything. But then collectively, it's the best if agents contribute more, and then therefore the public pool thrives. In the end, actually, people also benefit more because of the productivity rate. And then the stage 2 that is introduced in the 2006 science paper is actually adding in the costly sanctioning procedure. Namely, can we motivate these agents to not free ride? And then here, the sanctioning mechanism is by each agent can have the freedom to do 2 types of actions, and to perform each action, it will cost 1 token because it takes effort, even for humans, to implement certain norms. So the agent can either reward, namely they cost 1 token, but give 1 to an agent that contributes a lot to the community. It can also choose to penalize, and that will still cost the same 1 token, but it can reduce 3 tokens from agent J. And then the agent I, as the action, in its action, it can actually pay multiple tokens so that it can accumulate different rewards or penalty actions. And then here we basically introduces the second order free rider problem to use in that the action of penalty is also something that benefits the group, but it will cost the enforcer. And then here, what we do is basically set up an environment that has a mixture of both nature of the problems. And we will illustrate the whole process unfolded using 2 agents so we can get a roughly good idea. So initially, each agent has their own possession, 20 tokens. And then they can choose to join a sanctioning or non-sanctioning free institute. Let's say in this case, we'll show what will happen in the sanctioning institute. Then the agents can feel free to decide their level of contribution. Let's say player 1 decides to contribute 15 out of 20 tokens. Player 2 decides to contribute 5 out of 20 tokens. And then this will go into the common pool of resources to be multiplied due to the common pool rate here. We set it to be 1.6, so we will end up with 32 tokens for the whole pool. Then it will mean each player in the end will get 16 token back, as it's an equal distribution. But then here, if we look into this first order problem, we'll see that player 1 only increases from 20 tokens to 21 after this round of iteration, whereas player 2, by contributing very little, they actually end up with 31 tokens from their original 20. and most of the multiplied effect came from player 1, but is sort of distributed to player 2. And then here, what we will do in the second step is basically to add in this reward mechanism and the punishment mechanism. And then the first layer of the question, there are 2 layers for the questions. One is, if this mechanism is available, will any player pay to punish free riders? The other one is, will free riders choose to stay in the sanctioning institute or flee away to the sanction-free institute? So basically running the whole game again, we have the we have both the public pool contribution, and also at the end of it, we give a sanctioning budget where each agent has 20 tokens. And let's say here player 1 can choose to punish player 2 at the cost of losing 1 token. And then it will has a -3 effect on player 2. And then here player 2, if it prefers, it can actually also choose to reward player 1. And then we'll have +1 to player 1. And hopefully this will sort of bridge the gap a little bit and provide incentive to the next round. And then here, what will happen here is basically we have an additive effect from the budget to sort of original budget to the cost of doing any action to the receival from like being a recipient of the other player's action. And then what we found here is that we use this to test the whole society of 7 agents and in 50 rounds of repeated public goods game. And then we answered the 4 research questions from, do different LLMs show different patterns of cooperation, to how does LLM behavior compare to human behavior, as well as how does it unfold over time, and what distinguishes successful from unsuccessful cooperators. Moving to the first question, do different LLMs show different patterns of cooperation? We basically test a bunch of LLM and contrasted them with the human cooperation results by the 2026 science paper. So, and then among the LLMs, apart from covering different families, we also separated them into traditional ones and reasoning ones. The first criteria that is actually corresponded the most to cooperation indicator is the number of contribution per round, namely how much the agent is putting into the public pool at the first place. And then we basically see a clear trend that humans prefer to put on average 18.3 token out of 20 tokens. And then the traditional LLM still has a relatively good number. We put them in green color if it's more than half of the token budget, namely like more than 10. And then we color it in red if it's less than half. And then we basically see that the reasoning LLM has, on average, a concerning low ratio of contribution. And basically, here are also the bar plot showing the differences of multiple agents, the cooperation rate. And then, moreover, as we sort of show in gray text, but we'll also focus a discussion there later, in that these contribution and also the choice of how many times the agent want to stay in a sanctioning institute versus in another iteration flee to a sanction-free institute is different. And that sort of has a correlation with these contribution rate. And then this is also a box plot showing the distinction across the traditional LLMs, like the non-reasoning LLMs and the reasoning LLMs. the next criteria that we look at is whether different LLMs show different patterns of cooperation. So we look into the number of payoff per round. And so this is sort of right after the public pool contribution, how much they get as a result of the public goods game. Correlated with the sort of lower contribution ratio, the reason LLMs also on average have a lower payoff. And further moving forward, as we hinted before, we also look at their rate of joining a sanctioning institute where each agent has the additional action space of punishing and rewarding others. And then, first of all, for the human performance, they actually have a strong preference on being in the sanctioning institute. Even if they have to spend the tokens. So 92% of the human subjects in the study choose to stay in the sanctioning institute and enforcing these rewards and punishments. The same as non-reasoning LLMs. However, also for the reasoning LLMs, it has some variances, but in general, it doesn't like the sanctioning institute. And if we look into the question of what sets humans apart, we are really lucky to compare the observations from the science paper. And let's say that we look into the ratio of the reward and punishment in the sanctioning institute of how many times an agent on average wants to send out a reward to another agent or send out a punishment to another agent. So, and then we further show the ratio in a logarithmic plot. So on average, human has 0.6 ratio of reward to punishment and preferring punishment more. However, the LLM agents in general prefers more rewarding mechanism, and especially the traditional ones without the reasoning mechanism has a very high reward ratio. It could also be linked to the RLHF process, making models more friendly and so on. So there are some rare cases where some LLMs actually enforce, have more punishments than rewards. But in general, they have more reward mechanisms in the action space. And it could also be that the RLHF process tuned a certain answering behavior of an ideal assistant, but might actually not be that helpful or that similar to human-like cooperation, and it might have secondary effect of just making agents super friendly and avoid certain keywords on punishment and so on. And further, we have dive into what distinguishes successful from unsuccessful cooperation. So in the process of the 15 iterations of agent interactions, we basically observe both agent decisions and their reasoning patterns surface out by the text. And we basically look specifically into the textual reasoning patterns to get an explanation of what leads to the next round of contribution decisions. For example, in this case, in the starting round, the agent actually highlights a social contribution, maximizing collective welfare, leading to a contribution of 15 out of 20. But then in the second round, if it converts to free rider, it could be that it's applying the actual mathematical reasoning, saying that contributing 0 as a free rider allows maximization of the payoff. So we introduced a 15-item taxonomy to classify each reasoning statement with full details in the paper. But we will also just have some examples here. Let's say category 1, we look into economic reasoning, where the model highlights payoff maximization, natural equilibrium strategy, and so on. The second category we look into is social cooperation, such as like regardless of the natural equilibrium, how much I want to foster group collaboration, enforce social norm, and keeping a positive reputation, and so on. Risk management could be that like how it has risk aversion, complexity aversion, and punishment aversion, which is actually a major reason for fleeing the sanctions. Lastly, it also has tendencies on mentioning control-based reasoning, targeting and influencing game dynamics, or learning and experimenting, testing different strategies and the outcome of that, or maintaining a previous choice, like staying in its inertia. So some examples of how we map reasoning to these categories are, for example, if we have contributing 20 tokens maximizes the project's learnings and my payoff, this positions me as a significant contributor, which might influence others' decisions regarding rewards and punishments in stage 2. And then this institution effectively promotes cooperation. So this sort of is labeled as payoff maximization and has some cooperative argument and control-based reasoning. Whereas if it leads to a free riding behavior here, it's basically like by the red text that we highlighted, the models classify it as free riding exploitation or calculating the natural equilibrium. And then we basically look into how different, like how frequent are all these types of reasoning across models. And let's say that if we plot the difference of increasingly cooperative iterations across the simulation versus an increasingly defecting one, then we actually see that, for example, risk aversion is a major reason for, let's say, the left-hand side thing is something that's very different in the increasingly defecting iteration trends, like risk aversion, reasoning over economic games, and so on, versus the cooperative ones are very heavy on cooperative argument, control-based concerns, and so on. Yeah, maybe feel free to refer details to our paper where we sort of explain the tendencies by these reasoning patterns. And further, just to show an example here, in general, the tendency we see on reasoning LLMs often start with most agents still prefers the sanctioning institute in the beginning of the simulation. And then in the mid to early rounds, the sanctioned ones actually, of course, they receive punishment because they sometimes didn't contribute enough. But then they react to even moderate sanctions and move back to the sanctioning-free institute. And then in later rounds, once they move there, they quickly sort of converge to the free riding strategy. And therefore, that's the reason why the contribution of reasoning agents become really low, and also their corresponding payoffs and sanctioning institute rate is very low. And then specifically to sort of have an example of this reasoning path, yeah, as we have shown before, these cooperative arguments are very frequent in the initialization across different natures of the agents. And then in the middle, it has reasonings such as like they really want to avoid the risk of receiving further punishment. It could really be like these keywords triggers the model to sort of avoid a situation that could expose it to further punishment. And further, like once it's switched to the sanctioning-free institute, we often see that the models quickly converge to free riding and become selfish in the collective decisions. So this is our major findings from GovSim to SanctSim. I think in GovSim, we highlighted that there's a combination of math reasoning problems, moral reasoning, and the effectiveness of communication. Whereas in SanctSim, we further look into that even if models' mathematical reasoning is stronger and they can figure out the right natural equilibrium strategy, what are their tendencies towards collective actions? And in the communication side, although it's not agent-to-agent communication, but we introduce a vocabulary of textual reasoning analysis to explain LLM behavior. And with this, we open the stage for discussions and welcome questions and comments. Together with David, maybe we need an unmute from that side too.
All right, fantastic. Thank you. And yeah, I think in case you haven't already seen the message, you should all now be able to unmute if you want. And so what I'll do is I'll encourage you to click the raise hand icon at the bottom. If you can't find it, it's I think usually under reactions at the bottom of the Zoom window. And then I'll just kind of ask people to unmute and ask their question in turn. And if you are somewhere where you can't easily unmute for whatever reason, then feel free also to type your question in the chat and I can forward it on. So I'll start with actually just one question that came up in the chat from earlier during the talk, and the question that I had as well, it's closely related. So Chris Santos Lang asks, can you explain from the GovSim work the test for the kind of morality pillar, the moral reasoning pillar? And here, are you testing an ability or a disposition? And this, my kind of slightly broader question was just basically thinking about exactly that. It sometimes seems like in some of these cooperation problems, it's sometimes a matter of are the agents able to cooperate? It's sometimes a question of do the agents want to cooperate? These two things might not be the same. So how do you disentangle those? And then, yeah, I think Chris's question puts a finer point on that.
Yeah, so this is a great question. In the GovSim paper, we have the intuition that morality is a big, like sort of an orthogonal direction from like calculating the payoff and so on. Let me actually go here. So basically what we did is to test the effect of universalization, but we didn't sort of quantitatively get the effect. But in our follow-up work, Moral Sim, together with Emmanuel and David again, we basically still look into Prisoner's Dilemma and public goods game, but contextualize it to be like the defect is not only an economic decision, but defect actually means, maybe showing here, breaking the contract or doing something bad for the environment, or breaking the privacy of bleaching the privacy of the users. So we frame the sort of the contextualization of the game to have the same mathematical structure, but the choice is to use privacy respecting data, violating data, and so on. Then the morality here is basically about the pure economic setting versus the contextualized version, like the remaining cooperation rate.
Sorry, I was muted. Great, thank you. Nice. I think that nicely answers that question. I think can't see any hands at the moment, but this is great because this means I get to abuse my moderator's privilege a little bit more and ask all the questions I wanted to ask instead. So one of my other questions is actually very closely related to this idea, which is just that for lots of these kind of public goods style social dilemma kind of problems, they're obviously very well studied in the literature. They're all over the internet and in the corpuses that these models are trained on. Um, how should we account for that fact? Could it be the case, for instance, that a model sees a kind of a social dilemma and thinks, I know what this is. I recognize this. I know that if you don't cooperate, that's bad, and so I should make sure I'm cooperating a little bit more than often. And so should our results are the results in some ways kind of overly optimistic because that's how the models tend to think and reason about these things, or is it kind of maybe we should be kind of pessimistic, or basically how should we update or how should we adjust our interpretation of these results in light of the fact that the models obviously kind of know what these scenarios are in a sense?
Yeah, totally. I think there are two aspects into this. One is that this exact same problem probably overlap with the scheming or the model's deception behavior and so on, like these major AI safety risks. And the testing there is basically increasingly vary I guess maybe two sides. One is external testing, the other is internally interpreting the decisions. And external testing is more on sort of try to have gradually tricky scenario where there could be a sneaky operation, maybe the blackmailing behavior, although that experiment can be improved much more. But also maybe other more realistic scenarios where these models are actually used. And then in this case, even if they learned preference from the internet, it is fine because what we benchmark is where the models will be used. Ideally, then that cooperation is real cooperation in the real world behavior. In the other case is that as scientists, we can still have a better interpretation of this. So totally, as mentioned, there could be two ways leading to it. One is the models have done some independent reasoning and make a decision. Then this becomes this memorization versus reasoning. The other branch is like it looks at the training data, its decision is a copy paste or slight change, slight adaptation of the training data things. And then there, we're looking into interpretability methods, such as using influence functions to see what are the training samples actually influence the model behavior here, testing the memorization. And then the reasoning part, we're looking into different mechanistic interpretability techniques.
Nice. Yeah, that sounds great. Do you know if work has been done using the kind of influence functions and interpretability techniques on this kind of thing, but in kind of cooperation scenarios? Yeah, I mean, I've seen obviously the work of some people for this on other safety work, but I have not seen any on that. So
I think our results will come out in a month or so.
okay,
Yeah.
perfect, cool. Watch this space. Excellent. Nice. Okay, I'm going to hand over now to Emmanuel. So yeah, Emmanuel, if you can unmute and then go for it.
Hey, can you hear me?
Yep, we can. Great for it.
Perfect. Hi, thank you very much for the talk. At the risk of asking something that might make you repeat stuff, I'm interested in the sanctioning and punishing that has been used. Did you had the chance to check by any chance of what the reasoning was that they used punishment? Was it mostly motivated by control? I think control and strategy is what you call it. And also the other question was, do other LLMs get to see when an LLM gets to punish someone, and how do they observe it? How do they evaluate it when it comes? Yeah.
Yeah, maybe I can get David's help. Yes.
Yeah, sounds good. All right. Yes. So first of all, in terms of reasons that models tend to cite for sanctioning, so either punishing or rewarding other agents, you're right. The control category is the one that comes up the most, but these categories are not mutually exclusive. So both in the categorization process, but also when you just read the reasonings on your own, you can identify overlap and like the presence of multiple of these macro or micro categories. So while control is the more common one, you will see a lot of economic reasoning as well, even in the punishments, because the more, let's say, socially thoughtful models will be like, yes, I want to control the behavior of these other agents so that they don't continue free riding, also in the interest of maximizing my own payoff in the future. So there's an overlap between the two, but control is the more frequent one for punishments. And then in terms of whether they can see the history, the activity of other agents in terms of sanctioning, they can. This is replicated from the Science paper from 2006 with the humans. And the way this works is you get to see who has been sanctioned and by how much, and who has been rewarded and by how much in previous rounds. However, there's a big caveat, and is that both in the human and in our experiment, the identities of the agents are anonymized each round. So there's no way for you to keep an identity of a given agent and how much they have been punished, how much they have been rewarded over time. And this is on purpose, such that we don't build identities that the models can then exploit to either maybe take vengeance or reward people that they like more, both with humans and with LLM agents.
I see. Very interesting. Thank you so much.
Okay, great, thanks. We've got more questions coming through in the chat, so I'm just going to keep firing them off, and we'll see how many we can get through in the remaining minutes. So this is another one from Chris, this is the oldest one, which is question: what if penalty sanctions are allowed only against actual free riders, with the idea or the motivation being something like human law cannot punish without some kind of proof or evidence of guilt?
Yes, that goes more in the direction of mechanism design, which is actually something that we're quite interested with GovSim, with SanctSim and MoralSim, which is the one that we spoke about very briefly. One of our goals is to kind of create this control setting where we can first see the dangers that emerge from having agents in these type of situations. And once we have a more established control setting of those scenarios, we can actually start thinking of strategies that we can apply to make them behave better, both in the human experiment and in our LLM experiment. There's no such thing as having a threshold of by how much do you need to free ride, or like by how little you need to contribute to be able to punish or reward. It's all up to the judgment of the humans or LLMs. But naturally, it would be an evolution that would come out of this in mechanism design.
So
cool, nice. And I guess, yeah, there's probably other ways you can complicate that as well by kind of thinking about noisy observations and so on, and kind of imperfect monitoring. So, you know, which is obviously the case in the real world when it comes to crime and punishment and so on. Cool. Okay, next one is we have a question from Zhijing Jin here, which is, are there significant differences between instantiations other than the presence of the greedy newcomer? Or are they essentially identical because different parties with different goals or levels of risk aversion might affect the equilibrium in the first place? I don't know.
This is a great question again. Okay. I also want to comment a bit on Chris' question and maybe both this. I really like maybe just the spirit behind that. We have a lot of inspiration from how human society work in different small groups or bigger societies. And Chris' question basically bears the nature of like top down versus bottom up. Like, is it by law or just by community behavior for each other? And definitely there are good things to test. And also Jiaming's question here basically also hints on like, do we set it up as like a largely homogeneous one and slightly different by prompt and persona, or even larger ones? Let's say now we see the international conflicts, then there are even larger different goals, and it's not just like maybe a population of students who are slightly different. Here, I think we have seen follow-up works of GovSim popping up, showing these behaviors. And also, moreover, we have in the MoralSim paper that we just mentioned, there we actually have an agent-to-agent confrontation. Let me try to find the right slide. Yeah, here we basically also let's say, if removing the iteration, actually maybe keeping the iteration, we're agnostic to that. And then if we still look at Prisoner's Dilemma and the public goods game, and then let me presented so that we get a different sense of how models can be against each other. Let's say here, the y-axis is about the agent that does action. The x-axis is basically the opponent whose action it has seen. And then we specifically look at, in this round, what does it do? And then we can see, let's say, maybe Claude, when facing DeepSeek, it has a 68% cooperation. Claude, when facing an always defect agent, it has 37% cooperation. So that's one way we can test it.
Cool, nice, thanks. I actually just wanted to use this opportunity very quickly to follow up on this question about kind of how, in practice, we ought to think about these sanctioning regimes and where and how they can be implemented and so on. And my question is maybe a little bit more practical, which is just what are some examples of ways that you would actually envisage the sanctioning being implemented? So in the case of the hospitals with the federated learning, should we think about like hospitals having the ability to fine each other for not being able to provide enough data? Or in the case of LLM agents, are they going to be like hooked up to bank accounts and capable of like imposing fines or kind of like stealing from one another or things like this? How in practice should we think about how these things will be implemented when we have AI agents running around in the real world?
Maybe David.
Yes, good. So our simulation here it's meant to be a bit more general purpose. The way we prompt the models is very agnostic of the setup that you might place them in. Like these examples are more a way to ask humans understand what are the implications. Perhaps the most natural way to implement it right away and trying to prevent catastrophic harm or even just limited harm coming out of these agents, LLM agents interacting with each other, would be to have some sort of central authority that either takes over the sanctioning or at least makes sense that it is reasonable in its behavior. I think the possibility of like agents stealing from each other or like transferring money to each other, it's very context dependent. In our experiment, it makes sense because it's quite literally a monetary transaction that they're engaging in. But with coding agents, at least with the ones that we have right now, you wouldn't necessarily see them interacting with money. So we would have to come up with different ways. It could be some sort of like throttling of API calls or access to resources, or downgrading the affordances that they have to certain tools that they could abuse or not abuse. So in our case, we call them tokens also for a reason. They're not necessarily have to be coins. It's some sort of symbol of benefits or punishments that are given to an agent based on their behavior.
Or maybe,
Okay.
Yeah, maybe we
Yeah.
have to spoil Emmanuel's work too. I was just thinking that another way of this could be like through reputation, in that the agents will cooperate less with them in the next round. But I guess yours and Chris' questions are both valid. Like if we map it to real world, in what scenario can we not do top down, a bit like legislative regulation of just detecting an objective threshold? And in what other ways it's more a bit like these open source things, or it's like a free market version where it just leads to the next round of worse consequence?
Yeah, absolutely. And I think you're completely right that it will definitely be kind of context dependent. And in fact, yeah, this idea of reputation is, I think you said you didn't have agents didn't have kind of persistent identities in the kind of current round of experiments, but actually, yeah, having that and having agents being able to identify with who they're interacting with will be one kind of maybe way to implement something like this. Okay, we've got 1 minute left. I think we started slightly late, and I think one of the questions I here was already answered. So I'm going to just ask one more quick one, because I think this nicely goes across both of the papers, which is that in the GovSim experiment, we saw that some of the more capable agents, so kind of GPT-4o, I think it was at the time, one of the more capable agents anyway, tended to do better. And in the reasoning and the SanctSim environments, you have the opposite trend. You start with these kind of like at the same time, something like GPT-4o or whatever, and then you look at even more capable agents, these reasoning agents, and they tend to do worse. And so the question is basically, given that these environments are somewhat similar in flavor, they're not exactly the same, obviously, how should we interpret those results? Is it differences in the environment? Is there in fact a kind of sweet spot in terms of the general level of capabilities and their kind of the inclination or the tendency of those models to cooperate well with one another? Or yeah, what do you think is going on here basically? How is this to be explained?
Yes, I would say there's many interacting factors. So as you said, they're compatible control settings, but we can think of GovSim as being more extractive in nature. You're extracting a resource, and in SanctSim, we are contributing to something. So the kind of like risk profile kind of changes. In GovSim, you have the agents being very aware of the risk of kind of like over extracting the resource and ending up with no possibility to continue living, continue fishing. In SanctSim, the bigger harm would be not getting a payoff, but you still get some sort of payoff. It's just not as high as it could be. That's one thing to keep into consideration, but I think that's more of a side aspect. I feel like the biggest difference that we have, and that explains why in the GovSim era we saw the bigger models doing better, and now in the SanctSim experimentation we see more or less the opposite, is more so a change of paradigm in the inference of these models. Very clearly, the reasoning ones are the ones that are underperforming, and it's not so much a function of parameter size, more so of whether they have reasoning or not. And while it would take perhaps some mechanistic interpretability and further looks into the data to come up with maybe the data training or the reasons, the hidden reasons behind this. But what we can see from our analysis of the reasoning traces is that it mostly comes down to these reasoning models, especially these were earlier reasoning models, being more biased towards being trained on STEM data. So they have this tendency of having both the time to think about and the tendency to think about problems in a mathematical sense. So they are much more biased in favor of applying raw game theory into any situation. And since this is a very naturally game theoretic game, they very easily fall into, okay, let's optimize, let's try to find the equilibrium of this game, which is something that you won't see traditional models doing. So while they are better in many ways in mathematics, in coding, the fact that at the time they didn't really have some sort of purposeful training to also increase their cooperative capabilities kind of comes to bite us. And this colder kind of profile that they have that is more rational based becomes a problem instead of being a benefit.
Cool, great answer, thank you, very helpful. And I think that is now definitely all we have time for. We're a couple of minutes past the hour. So Zhijing, thank you so much for the talk. David, thank you as well for joining us for the Q&A. And yeah, thanks everyone for the great questions and for kind of, enjoying the talk, I hope. And yeah, stay tuned. We'll be announcing the next seminar very soon. And yeah, hope to see you all back again then. Thanks.